when we were looking at we ended when we were looking at the linear PDFs, and we wanted to generate the PDF or the expressions, the equations of the PDF from the graph of the PDF. So we had an example, that was saying that we ended on this, finding the PDF given the graph of the PDF. So given the graph of the PDF, the PDF, smaller f of x or smaller f of any variable can be found by using the knowledge of the equation of the line, like we wrote in our introductory statements. So we had an example that was saying that below is the graph of the PDF, smaller f of x. This was an example, and this was our graph. This was the f of x. So this was a k, this was a 0, this was a 2, and then this is a 4. So this is a 1 and the 8. So the very first step was, for the very first question, where k was a constant. The very first question was to find the value of k. And since this is a linear PDF, we said whenever you have a linear PDF or the graph of a linear PDF and they want you to find the value of that unknown, then the area under the graph represents the total probability for which the PDF is defined, and our total probability must always be 1. So the total area under the graph should be a 1. So in our solution we said that if this is the linear PDF, this is f of x, this is 0, this is k, this is a 2, that is a 4. We said that before doing anything, you first shade that area under the graph of the PDF, which is this part here, bounded by the x-axis and the f of x-axis. So after shading that region, then you say that the total area shaded should be 1. You don't shade it from the original question, but you write or you redraw the PDF with some paper very fun. They may come and shade where they have written the example and it will lose meaning. So you redraw and then you shade. Then you say the total area shaded is a 1. So after saying that the total area shaded is a 1, you go and look at the structure of the shape that has come out as a result of shading, because this was already given. And our structure is a rectangle, that shape, it is a triangle. That shape is a triangle. And since it is a triangle, a half BH should be a 1. You may separate this into 2, or you can treat it as one triangle. You may say this is triangle A, this is triangle B, or you can take it as one triangle. And because you are the most intelligent, we are going to treat this as one next step, we have other values here for consistency. It is running from 0, 1, 2, then 3 and 4. But our interest, this x is representing the x-axis. Our interest is from where it starts and where it ends. This line here indicates that the PDF is defined from 0 up to 2. So we have the interval. For the interval from 0 up to 2, we are putting here x because this is x. If it was t, we would put there small t. Now for the interval from 0 to 2, the line from here up to here, you read off the coordinates here and there. The first set of coordinates here is when x is 0, y is also 0. The second set of points here is when x is a 2, y is a half. Then the last set of points here, or coordinates, at this point is 4 and 0. After putting all the coordinates there, remember our focus was on the first one, which was running from here to here, from here to here, and its interval is from 0 to 2. We can't say it is from 0 to 1 because the line is still progressing. That is why we are saying it is from 0 to 2, because after reaching 2, it changes course, and it changes the direction, and it is now descending. So from 0 to 2, we are going to use the coordinates 0, 0, and 2 are half. The equation of a straight line that connects 0, 0, 0, and 2 and a half will be the function of the PDF for the interval from 0 up to 2. So the first step, we are going to assume another variable point x and f of x lie on the same line. So if you call this point A, point B, and point C, we are going to find the equation of the line passing through AB and C. Now find that equation. Find that equation of a straight line. We going to gradients. We have 3 points A, B, and C. So you equate the gradient of AB, the gradient of AC. You always make this first point to be common. But what we know about collinear points is that they have the same gradient. All points lying on a straight line, the same straight line, they have a common gradient. So the gradient of AB is the gradient of AC. Or the gradient of AC is the gradient of AB. So you pick any set, but me, I would prefer to take that. This is method 1. There is another approach getting the equation that we shall see. So this side we have AB, and of course because it is gradient, it is going to be changing y over changing x is equal to changing y over changing x, which is y2 minus y1 over x2 minus x1. It's y2 minus y1 over x2 minus x1. Now, we suppose that y is a function of x, and all these second points, if they are taking on the y values. Because this is A is the initial point, and B is the last point. It means point A, which is the first one, has x1 and y1. And point B, which is the next one, has x2 and So in method 2, this is now method 2. We are on the same interval from 0 s equal to 2. Method 2 of getting the equations of the PDF. We are supposing that our y is f of x. We know that the general equation of the line is given by y is equal to mx plus c. But now this time our y I'm using only one method, then for you, you can write one in the first interval, then you still apply it for the second one. So for 2 is this equal to x, this equal to 4. It is splitting from this up to this. We now reach the corresponding points which are at the respective points where the function starts and where it ends. The first point is 2.5, and the second point Now for all other values of x, we call it 0 otherwise, or 0 elsewhere, and that is the PDF. Now sometimes you might have some other question that follows that, and it is about finding probability. So I request in our respective homes you try and find. We discussed how to get the probability using the graph and also using integration of any continuous one-to-one value. So normally you try to use the knowledge of finding the probability using integration, some of you. Then the others can choose to use the integration, and you calculate these ones. Then you shall compare the answers in our respective groups, check whether they are correct. Then still in your free time, you can try out this. It's a try question. It says that below is a graph of the PDF, small f of t. You see, this time it is not about x. You see, most of you are used to your x's, but now this time it is about the t. And this is the graph. If this is f of t, then this is a t. It stretches from -1, 0. We have 1 and 2. So it runs from -1 up to 0. Then from 0 up to a 2. This is a k. Then this is 2k. said to be linear if the highest power on the variable in which it is defined, it is a 1. So if the highest power on the variable in which the PDF is defined is a 1 or a 0, then it is linear. Otherwise, it is nonlinear. Otherwise, to me, if it is 2 and beyond, or if it is a negative, for example, if f of t is t power negative, this is nonlinear. If f of t is t power 3, it's nonlinear because the power of t is not a 0 and it is not a what? A 1. But if f of t is maybe 1 over 7, this is linear because having 1 over 7 as a constant is as good as having 1 over 7 t, the power 0. So we want to deal with the nonlinear ones. Now, if you have a nonlinear PDF and you want to sketch it, you begin by doing the following. So these are the steps. You begin by finding, of course, you identify f of x, that is if the PDF is defined in terms of x. You identify f of x in the different intervals. Why choose to identify it in different intervals? It is because in one interval it might be linear. When in the other interval it is nonlinear. So you cannot define it in only one interval and stop there. And when it is linear, there are steps that we follow. When it is nonlinear, there are these steps that we are supposed to follow. So we discussed when it is linear. Now, if it is nonlinear, what is nonlinear? If f of x is nonlinear, then what? Step 1 or step A, we find the values at endpoints. So whether it is linear or nonlinear, we must always find the values at endpoints. Then B, we find the turning points. And of course we find them, and also we find the turning points and also determine their nature. We determine whether it is a minima or a maxima. In most cases, it must be a minima or a maxima. But there are those small cases which are even rare. It has never happened where it is a point of inflection. But we are going to see how we will realize that it is a point of inflection, how we realize that it is a minima, and how we realize that it is a what? A maxima. So in step 2, find the turning points and determine their nature. So how do we determine the turning points? We discussed from pure mathematics that for you to get the turning points, you differentiate the original function once and equate the derivative to 0. Why do we equate the first derivative to 0? Because whenever we substitute the x-coordinate of the turning point in the first derivative, it is we get a 0, implying that we always determine the course, the changes in the slopes on either ends of the x value by picking values before and after. So that is why we always shaped or n-shaped, or it is an inflection. So you are finding the turning points, but we are also noting that to find the turning points, you equate the first derivative to 0. After finding it, equate it to 0. When you equate it to 0, you get the x-coordinates of the turning point. Then you substitute the x-coordinates of the turning point in the original function. Then you get the corresponding values of f of x, implying that my turning point will definitely be x, f of x. Why equate the first derivative to 0? This is to find the x-coordinate of the turning point. So when you equate the first derivative to 0, you get the x-coordinate of the turning point. After getting the x-coordinate of the turning point in step 1, substitute that x-coordinate in f of x and you get the y-coordinate of the turning point. Part B. Now to determine if you want to determine the nature of the turning points, we can determine the nature of the turning points by getting the first derivative and differentiating the second time. So we use the second derivative to determine the nature of the turning point, or we can use the sign of dy by x, which is the sign of the first derivative of the function f of x. So in method 1, we are using the second derivative. If you differentiate the original function twice and you substitute in the x-coordinate of the turning point, if you get an answer, I'm supposing my turning point is x1 f of x1. If you substitute in x x-coordinate of the turning point, you pick a value on its left, and that is a value which is less than x1. You put it in the first derivative and you check the sign. You pick another value on its right, and that is a value which is greater than x1, but you don't pick a value which is very far from the x-coordinate of the turning point. If it is a 2, you may pick a 2.5 or a 3 and you test. Then the one which is less, you can pick 1.9, 1.5, but you shouldn't pick the one which is very, very far. So after picking the x-coordinate, because this is not known, now we are going to assume if the x-coordinate x1, if you pick an x-coordinate which is less than x1 and you substitute it in f prime of x and you get a negative, you get a 0. But when you substitute in the one on the right, you get a positive. A negative slope moves like this, like this. When it is 0, it is a constant. When it is positive, it moves like this. So if it forms a U-shaped curve, it means that the turning point x1, f of x1 is a what? Is a minima. Because it is forming a minimum value of y or of f of x. You may still substitute in that, but instead form an N-shaped curve. So this is when you employ and it follows that pattern. But you can as well employ the x-coordinate for the whole volume. When you employ it and you get the x-coordinate